Suppose it is given that two deuterium is combining and formed helium 2,4. Okay. So the constituents of helium is 2 deuterium, right? So 2 deuterium is combining and forming helium 2,4. It is given that the nuclear mass of a 1s2 nucleus is given as, okay, that is 2.01355 atomic mass unit, right? And the nuclear mass of a helium 2,4 nucleus is given as 4.00260 atomic mass unit U. Okay. So to calculate binding energy per nucleon of helium 2,4. So notice here, what the thing is interesting here, the constituents of helium 2,4 is given as basically forming by two constituents, that is 2 deuterium nucleus. I mean, okay. So binding energy of any nucleus basically depends upon its constituents. So suppose अगर इस तरह की केस देते आपको, सपोज मान लो कि दैट हीलियम इज बेसिकली फॉर्मिंग बाय कंबाइनिंग 2 प्रोटॉन and 2 neutron. They're combining and making helium 2,4 nucleus. तो यहाँ पे constituents क्या है आपका? 2 proton and 2 neutron, they are combining and making helium 2,4. ठीक है ना? तो इस केस में जो बाइंडिंग एनर्जी पर न्यूक्लियन होती है इसका, that will be different from here, because here you have a constituent that is given 2 deuterium. So binding energy of any nucleus depends upon its constituents. So as you know, to calculate the binding energy of any nucleus, just you have to calculate the mass defect. Before calculating binding energy of any nucleus, you have to calculate mass defect, delta M, right? And that is nothing but mass of, or you can mention also nuclear mass of constituents minus actual nuclear mass. Okay, is it clear what I'm saying?
Yes, sir.
Okay, now you see that actual mass of constituents means you have a constituents that is 2 nuclear mass, or I'll write that mass of 2 times mass of on H2, that is the mass of constituents. You have a constituents that is 2 deuterium. So mass of the constituents minus mass of the, or actual mass, an actual mass of what? Helium 24. So depending upon composition, अगर इस केस होती तो फिर क्या लिखते हम? 2 times mass of proton plus 2 times mass of neutron minus actual mass, that will be the mass defect of this fellow. But here you have a constituents like this. So mass of constituents minus actual mass of this fellow, that will provide you delta M. If you multiply it by C square, that will be binding energy. And if you divide by mass number, then you will get the binding energy per nucleon of this nucleus. Is this clear what I'm saying? क्या clear है?
Yes, sir.
Okay, good. So just I'll write the delta M here, and that will be 2 times mass of a hydrogen atom, and mass of a deuterium nucleus, and that is given as 2.0 on 355 minus mass of a helium, and that is given 4.00260, right? And in the unit of atomic mass. Okay. To calculate this value, basically you will get 0.0245 atomic mass unit. Okay, you can check also. So this is the mass defect of helium-24. Now you can calculate binding energy of helium, right? And that will be how much? That will be nothing but delta M into C square. And delta M is provided that we have calculated actually. That is 0.0245 U. From U you have to go to MeV per C square just by multiplying 930 on 0.5, and that then it will be mega electron volt per C square, right? And you have already another C square here, and this will be cancelled. It will be cancelled. Okay, and you'll get the binding energy, and that will be, if you calculate, you'll get 22.82 mega electron volt. Okay, and you have to calculate binding energy per nucleon, right? So you have to divide by how what? You have to divide by what?
Number of nuclei
How many are there?
divided by 4.
Exactly. You'll have binding energy per nucleon. It means you have to divide this number by 4. And if you calculate, you will get
5.71.
exactly. Okay. So actually what I'm trying to say here, that binding energy per nucleon actually depending upon its constituents. Okay. If there is constituents like that they have given, you may get some different values. Is this clear to all? हाँ ना बोल दिया करो.
Yes, sir. Clear है.
Okay, thank you. Okay, we'll go to next problem. In that question, it is given that the binding energy, total binding energy of neon 1020, that is given. Okay, and that number is given as on 60.64. obviously unit will be mega electron volt. And also they have provided the mass of a hydrogen atom. Remember, it is given the mass of a hydrogen atom. You can write it properly. Given mass of a hydrogen atom, and that is 1.0078 U. And also given that the mass of a neutron, and that is 1.0086 U. So what you have to calculate? You have to calculate the atomic mass. The atomic mass of neon 10, 20. कर लोगे? Is this can be done?
Yes, sir. कर लेंगे.
Tell me the how will do that?
So पहले bending energy is equals to
Exactly.
delta T square.
It is exactly. So
Delta
you see
M
here,
nuclear.
आपको क्या पूछा गया है? Not nuclear mass. You have to calculate atomic mass, right? But we know that mass defect in terms of atomic mass, है ना? क्या formula होती है? So you know that binding energy is nothing but delta M into C square, and that delta M has actually two different formula, right? In terms of atomic mass, also it has some formula in terms of nuclear mass, right? तो यहाँ पे आपको atomic mass calculate करनी है. So what I'll use the delta M. क्या use करेंगे हम? Z MH, right? Plus N Mn, and then you will have mass of atom, right? And you will have C square here. So if you write that mass of, if I write the atomic mass of neon, it will be how much? Z, कितना Z है? 10 exactly. So 10 into mH, and that is given 1.0078, and then you have, so this unit is basically what? Atomic mass unit, right? Then you will have N, that is again 10, Mn, that is 1.0086 U, right? And then we will have binding energy, and that is given 160.64, right? That is unit is given mega electron volt, और नीचे क्या आ जाएगी?
931.5.
Exactly. You are going faster than me. Okay, so you have a, first of all, you have a C square, right? Because you are bringing this C square this side, you have a, first of all, what you are doing? You are dividing by C square, right? You have a binding energy past C square. Binding energy.
Sir, we will subtract also, no? Minus M mass of atom.
Haji? Yeah, we have subtracted. You see, this from the here I am writing this. Just मैंने क्या किया? First of all, देखो, मैंने C square से divide किया.
Yes, sir.
Binding energy past C square, right? You have this on the left hand side. अब मैं लेफ्ट हैंड साइड का ये बाइंडिंग एनर्जी को
अंडरस्टैंड
वेरी गुड
समझ गया.
हाँ, अब टेल मी ये जो होगी MEV पर C square, ऑन MEV पर C square क्या होती है? फिर रिमेंबर ऑन एटॉमिक मास यूनिट इज नथिंग बट 930.5 MEV पर C square, राइट? नाउ ऑन MEV पर C square कितना हो जाएगी? ऑन बाय 930.5 एटॉमिक मास यूनिट, राइट? सो एक MEV पर C square को हम क्या लिख सकते हैं? ऑन बाय 930.5 एटॉमिक मास यूनिट. So you have MEV per C square. You can convert this MEV per C square in the unit of atomic mass unit just by dividing 931.5. So if I do that, then my life will be simple because all unit will be now atomic mass unit. So if we divide by 931.5, then this unit will be atomic mass unit. Okay, now your job is done. Just you have to do some simple calculation, you will get that atomic mass, right? and that will be 19.99 U. Okay, is this clear to all? Tell me. कोई डाउट है?
No, sir.
Well, so now another problem we'll do, then we'll go to the next topic. Can I take a test?
Yes, sir.
Okay. Tell me the time when I'll take. Within a week? Okay, आप prepare करो, है ना? Within a week, I'll take a test. Okay, next problem. जब तक टेस्ट नहीं लेंगे तब तक रिवाइज नहीं करोगे ना? I know. Okay, so second last next problem is we have a binding energy per nucleon curve is given. Of course, that will be mega electron volt, right? Nah, the binding energy per nucleon, the unit of mega electron volt is given, and that curve is look like this corresponds to 2 mega electron volt. This corresponds to 4, and this height corresponds to 8 mega electron volt, and this corresponds to 6 mega electron volt. The binding energy per nucleon curve is given. And this height you can understand. 2, 4, 6, 8. And this mass number is like 20. And then you'll have 40. Then you'll have 80. You extend something more, then it will be more fine. It's not proper representation actually. You will have like this. On 20. And you have mass number up to 200. क्या दिख रहा है कर्व? Was going outside. ना इसको extend करो up to 200. It's a constant height. From 120 to 200, there's a constant height, and that binding energy value or binding energy per nucleon corresponding to this height is 4. And a parent nucleus, of mass number A equals to 180. So parent nucleus mass number 180 undergo nuclear fission and break into 2 nuclei B and C, and their mass number are equal. It is given. So a parent nucleus, they provided this binding energy per nucleon curve. A parent nucleus mass number 180 undergo nuclear fission and break into 2 nuclei, light nuclei, having equal mass number 90. So you have to calculate for this process how much energy will be released or absorbed. How much energy will be released or absorbed? कर लोगे? So you know, as you have discussed, that if the binding energy of the product is greater than reactant, then there will be release of energy, right? So just nothing is there. You have a binding energy per nucleon curve. You have to calculate total binding energy of reactant and product, and you have to subtract from product binding energy to reactant. And if you have positive sign, it means there will be release of energy. If there is a negative sign, there will be absorbed in the energy. So tell me, how much will be the binding energy of reactant here? So per nucleon is how much? Per nucleon, you can see here, for 180 mass number, binding energy per nucleon is actually 4. And you have a total mass number, your mass number there is
180.
So total binding energy, if I calculate, for reactant will be 180 into 4, right?
120.
Exactly, 720. So it will give you 720 mega electron volt. And for B, it will be how much? 90 into kitna ho jayegi? I can see here 90 will be somewhere
4.
here, right?
4.
90 will be somewhere here.
19 to 6. 10 to 6.
Exactly. So 90 into 6, and then we'll have for C 90 into 6. So इनका प्रोडक्ट का अगर टोटल सम करोगे कितना आ जाएगी?
1000 DI.
Exactly. So it will be 1080 mega electron volt, and here you have 720. So binding energy of the reaction so that is product minus reactant, and that will be plus 360 mega electron volt. So there is a plus sign, right? Product is having a higher binding energy. It means, or you got the binding energy of the reactions having positive value. Yesterday also you have discussed, when you have positive binding energy in the reaction, there will be release of energy. There will be a release of 360 mega electron volt energy, right? There will be release of 360 mega electron volt energy in this reaction. Okay, is this clear?
Yes, sir.
Yes, sir.
Okay. Then you have another topic that is known as packing fraction. The earlier method to calculate or to investigate the nuclear stability, but now we use binding energy curve to investigate the nuclear stability. Okay, so this process is actually old, packing fraction. पहले ये यूज होते थे to understand the nuclear stability of a nucleus. But अभी क्या यूज होती है? That you know, right? We have learned details about binding energy per nucleon, and that basically tell whether मतलब बहुत सारे न्यूक्लियस में से कौन सबसे ज्यादा स्टेबल है, that you can easily understand from binding energy per nucleon curve. And it's an old process to understand that nuclear stability. So basically denoted by F. And what is F? Nuclear packing fraction, that is defined as actual nuclear mass, NuCl, minus mass number divided by mass number. So here MNuCl is what? क्या है NuCl?
सर डिवाइड में क्या है ए है ना वो
Exactly, mass number. So packing fraction of a nucleus is defined as actual nuclear mass minus mass number divided by mass number. Okay, so MNuCl is the actual nuclear mass. Actual nuclear mass. Actual nuclear mass. Okay, and that will be कौन सा यूनिट में होती है?
Atomic mass unit.
Exactly, that will be in atomic mass unit. Now you see A is what? क्या है?
Mass number.
Exactly, mass number. So हर एक mass number मतलब you have how many nucleons inside nucleus, right? So you have a like some mass and then you have a number. But ये आपका unit सारे का क्या होनी चाहिए according to the basic physics?
Same होनी चाहिए.
Same होनी चाहिए. So if you express that atomic mass number in terms of क्या होनी चाहिए? Atomic mass unit होनी चाहिए, right? A का unit क्या होनी चाहिए? Atomic mass unit होनी चाहिए, right? According to basic rule. So have a nucleon having mass number A. तो इसका A in terms of atomic mass unit में कितना होनी चाहिए? हर एक न्यूक्लियन का कितना मास है? Around 1, right? यह प्रोटॉन का कितनी होती है? 1.0072. यह न्यूट्रॉन 1.0086. So around each न्यूक्लियन का जो मास होती है around 1 atomic mass unit के बराबर होती है. So if you express that atomic mass number in terms of atomic mass unit, just you have a number of nucleons multiplied by 1 and that will give you अब ये बताओ जो स्टेबल न्यूक्लियाई है उनके लिए कौन सा बड़ा होगी? Whether this will be large or this will be large. So you express that you have a nuclear mass, right? You have a nuclear mass or actual nuclear mass here and you have a mass number. If you multiply it by 1, that will give you A in terms of atomic mass. Now tell me, क्या ये बड़ा होगी या ये बड़ा होगी? For stable. Exactly. For stable mass, stable nuclei, A will be large as compared to actual nuclear mass. So obvious, right? Because we have learned this thing in mass defect.
yes,
So it means for stable nuclei, when you will have, तो अगर ये बड़ा है इससे means you will have packing fraction that will be negative and that is for what? For stable nucleus. That is for stable nucleus. Am I right? We will have F equals to positive number and that basically representing or for
unstable.
exactly. Right? Okay, now it is experimental fact that as you have learned from binding energy per nucleon curve also, light mass are actually not stable and heavy nuclei is also not stable. So to expect that जो light mass होगी उसके लिए packing fraction क्या होनी चाहिए? Positive होनी चाहिए, right? Expect that, है ना? So we have learned this thing, right? For low mass nuclei, we have binding energy per nucleon low. I mean they are not stable. And also you have mass number is heavy or high, then binding energy is less. Binding energy per nucleon is actually less. It means they are unstable. So it means जो low mass nuclei होगी उसके लिए भी packing fraction positive होगी और heavy nuclei के लिए भी packing fraction positive होगी और intermediate के लिए packing fraction negative होगी. But सबसे कम किसकी होगी?
Iron का.
Exactly. Very good. So if you plot it, because iron is having highest binding energy and highest binding energy means what? It's more stable. It means packing fraction will be least. So if you plot it, that packing fraction as a function of mass number will have this kind of plot. So mass number below 20 and above on 80, that F is actually positive. Na? This is your 0, right? And the minimum value that corresponds to what? F mass number 56, 26 atom number. So basically from this curve, what I can conclude, that mass number less than 20 and mass number 20, they are basically what? Kya hogi? Tell me. Mass number less than 20, they have positive packing
Unstable.
and they are unstable. But except कौन exception है?
Calcium,
Calcium?
oxygen,
Oxygen.
neon,
2, 4. Then carbon 6.
And oxygen.
Exactly. Very good. And mass number in between 20 to how much? 180. They are stable. And mass number greater than 180. Again, unstable. Unstable. Okay. Now we have another topic, and this is really important to understand, that is known as nuclear force. Because everything is happening, or existence of nuclear, existence of nucleus, and that is the gift of nuclear force. Nucleus is stable because of only nuclear force. The topic will be now nuclear force. Nuclear force. To understand this, actually, let us calculate. Suppose you have a proton. Oh, sorry. You have two protons. Inside nucleus, they are actually at a distance of how much? 1 femtometer around, right? Nucleus के अंदर दो प्रोटॉन कितना डिस्टेंस में होती है? That is of the order of femtometer, right? Am I correct? हाँ ना बोल दिया करो.
Yes, sir.
Yes, sir.
So if you have suppose two protons are at a distance of 1 femtometer, can you please calculate that Coulomb force? Coulomb repulsive force. So you have a two positive charge at a distance of 1 femtometer. So there is a Coulomb repulsive, right? Because they are identical charge.
Yes, sir.
So if you calculate it, you will have 1 by 4 pi epsilon naught, right? And then you will have E square by R square, right? And if you substitute this in SI unit, 1 by 4 pi epsilon naught is nothing but 9 into 10 to the power 9, right? And then you will have E square, and that value is 1.6 into 10 to the power minus 19 chi square, right? And you have R square, and that will be 10 to the power,
1
Minus
into
10.
10 or minus 2.
right? You calculate this value, you'll get 230 Newton. Can you imagine? You have a two light particle. Mass कितना है दो प्रोटॉन की? 10 to the power minus 27, right? A two light particle, when they are at close distance of the order of femtometer, there's a huge amount of force, 230 Newton. Can you imagine?
Yes, sir.
And there's a huge amount of repulsive force acting. Right? So you have a huge amount of nuclear, Coulomb force that is acting on the proton. then why this force is repulsive, right? They repel each other by this much amount of force. Then how the nucleus stable? How the nucleus stable? And that is because of nuclear force. That is because of nuclear force. But the characteristic of nuclear force is quite complicated. There's no mathematical form. But if you see that experimental curve, the nature of nuclear force is not simple. It's quite complicated. So this side, you have a strength of nuclear force, Fn, that is of the order of 10 to the power 4 Newton. Of the order of 10 to the power 4 Newton. And along x-axis, you have a internucleon distance. Internucleon distance. You see that nature, it will be like around 1 femtometer. When that separation between two nucleon is around 1 femtometer, there's a force, attractive force, that is minus 2.5 into 10 to the power 4 Newton. So around 1 femtometer, there's a negative force, and that force is 2.5. Order is how much? 10 to the power 4. So when two nucleon are at a distance of 1 femtometer, there's a huge amount of force, huge amount of attractive force or attractive nuclear force is acting, and that is 25,000 Newton. And in front of that, 230 Newton is nothing. 25,000 on side, that is attractive, and Coulomb repulsive is only, this number is huge, but if you compare with nuclear force strength, it's not nothing. 25,000 on side, this side you have only 230 Newton. But another interesting thing is that when that nucleon distance, internucleon distance is increasing from 1 femtometer, there's a strength of nuclear force is decreasing, and around 2.5 femtometer, this force is almost negligible, almost zero. And 1 femtometer is the highest force. There's an exponential decay with increasing distance from 1 femtometer. Around 2.5 femtometer is almost zero. But if you see below 0.8 femtometer, this distance, below this distance, that nuclear force is what? Below 0.8 femtometer. When the internucleon distance is below 0.8 femtometer, there's a positive nuclear force. Positive means what?
Repulsive.
Exactly. So actually, what does it mean? When two nucleon are trying to come closer than 0.8 femtometer, the force that is opposite to come, that force is what? Nuclear force itself. Nuclear force will not allow to come two nucleon closer than 0.8 femtometer. Why? Because there is a repulsive force, है ना? आपने बाहर से तो कोई force नहीं लगाया न्यूक्लियन के ऊपर, right? कैसे हो जाएगी? There is attractive force, but जैसे 0.8 femtometer, then it started repulsive. It means two nucleon cannot come closer than 0.8 femtometer. And if it's not able to come 0.8 femtometer, within this region they will stay. I mean, they will stay within this distance. And around 1 femtometer, this force is quite high. So two nucleon cannot come below this range. Okay, they will stay within this range. Okay, how about the force is almost zero, around 2.5 femtometer. Now tell me if you have any doubt.
Sir, hence the nuclear force is short range force, na, up to 2.5 centimeters.
That's why it is called short transport.
Yes, short
That I'll
transport.
tell you, but tell me, is there any doubt on this? Because this thing is, I mean, I'm interested to explain you more because this is the main thing actually. Tell me if you have any doubt. No? Okay. Now, the mechanism behind nuclear force is successfully given by Japanese scientist Yukawa in 1935. Can write that also. The mechanism behind nuclear force. The mechanism behind nuclear force is given by Japanese scientist Yukawa. Okay. In 1935. What he said? He said the nuclear force is a result of continuous exchange of smaller particle known as meson, pi meson. He's saying that nuclear force is a result of continuous exchange of smaller particle known as pi meson. What he's saying that he said that neutron inside nucleus, neutron is interacting with neutron by the exchange of pi zero meson. In reaction form, I'll write you will have a neutron will interact with neutron by the exchange of what? Pi zero. In reaction form, it will be like this. He said that inside nucleus, neutron is interacting with proton by the exchange of pi minus meson. In reaction form, it will be what? Why I am writing pi minus? Anyone tell me? Tell me. हाँ या ना बोलो. So he said that neutron is interacting with proton by the exchange of pi meson. In reaction form, it will be n decays to p, and there will be pi minus. Why there is a pi minus here and here pi zero?
Charge on both the
Exactly.
sides.
You have to conserve the charge, right? And he also said that proton is interacting with neutron by the exchange of pi plus. In reaction form, it will be n decays to pi plus. P decays to n plus pi plus. He said proton is interacting with proton by the exchange of what? क्या exchange होगी यहाँ पे?
Pi naught.
Exactly.
Zero.
Okay. And that reaction is like so that this exchange is happening continuously. In 100 years back, it was happening. Now it's happening. 100 years later, it will happen. This process is happening continuously. But what we are learning that neutron is attracting with neutron by the exchange of pi zero. Neutron is attracting with proton by the exchange of pi minus. Proton is attracting with neutron by the exchange of pi plus, and proton is attracting with proton by the exchange of pi zero. So I can see from this diagram itself that nuclear force is actually independent on charge because proton is also interacting with proton. Neutral particle is also interacting with neutron. So from this exchange process, we can see or we can conclude that nuclear force is charge independent. But tell me, is this decay process is allowed outside nucleus?
No, sir.
No, never, because meson particle is actually not that much light. Meson का mass कितना होती है? If I write that mass of meson pi plus, pi minus, and you have pi zero also, कितनी होती है? हर एक का around 140 mega electron volt per c square. Okay, so light mass से heavy mass में convert होना possible नहीं है. It will violate that energy conservation. However, inside nucleus there is no problem. So in the exam they may ask you Is this decay process allowed in free space? None of them is actually allowed. Okay. Okay. Now you write that properties of nuclear force, and I'll ask one by one. Be prepared. Huh? I'll ask one by one. So first of all, nuclear force is what? एक property बोलो. मृदुल बोलो. एक property. What is the first property I can write?
Charge independent.
Charge independent. Okay. So first you write that nuclear force is charge independent. Deepak, second property बोलो. Can you hear me? Deepak, Sonu, Sahil.
Sir, short range.
Nuclear force is short range. ठीक है, charge independent, short range. Then nuclear force is non-central. Nuclear force is non-central. What is the meaning of non-central? Anyone? Nuclear force is non-central. What is the meaning of non-central?
ये किसी पर्टिकुलर सेंटर की तरफ वर्क नहीं करते.
So like you are explaining that English word, right? Tell me in more explanation. I mean, if a force will be central. Curve?
Angular.
No. Central force में आप पढ़े हो. That if the force is conservative, then it will call central force, right? Or I can say if the force is actually depends upon position, then it will call central force. But nuclear force is not actually only depends upon position, but also depends upon velocity.
तो वो सेंट्रल कैसे नहीं होगा, वो डिस्टेंस पे पोजीशन पे डिपेंड है ना. 1.8 सेंटीमीटर के पहले होगा रिपल्सिव.
No. Central force का मतलब वो नहीं है सिर्फ. वो तो एक पोजीशन डिपेंडेंट है, बट न्यूक्लियर फोर्स का सेंट्रल फोर्स कब बोलता है? जब कोई फोर्स हमेशा someone already explained that it will always act towards center. Or I can say that nuclear force, if nuclear force is if any force is only depends upon position vector, है ना? I think you learn in classical mechanics, right? If force is if it is depends only on position vector, then it will be called central force, right? And इसके लिए condition क्या होती है? If I express in more way, क्या होती है? That should be curl of f like this, right? Because to क्या होनी चाहिए? 0 होनी चाहिए. But अगर कोई force velocity के ऊपर डिपेंड है, then it will not be central force. Is this clear what I'm saying? I mean, you will not get this kind of word in a textbook. That's what I'm saying. Is this clear? No?
Yes, sir.
Okay, next. Next you have that nuclear force is spin dependent. Nuclear force is spin dependent. The meaning of spin dependent?
Depend upon the spin of the nucleus.
So each you know that inside nucleus you have a neutron and proton, right? So each is having spin. अगर सपोज मान लो दो न्यूक्लियन है और दोनों का स्पिन s1 s2 that is half. If they are parallel, then for them that nuclear force is high, Fn will be high. Fn will be high. But if they are anti-parallel, then Fn will be low. Okay. And I can give that expression also. Nuclear force F n actually ऐसे लिखा जाता है. Some constant value k, and with you have s1 dot s2. s1 dot s2 का mod. Expectation value, then you have mod. कर लोगे, यहां से प्रूव कर सकते हो कि न्यूक्लियर फोर्स जो है जब दोनों स्पिन पैरेलल है उसके लिए न्यूक्लियर फोर्स ज्यादा होगी, जिनके लिए एंटी पैरेलल है उनके लिए न्यूक्लियर फोर्स कम होगी. फ्रॉम दिस वैल्यू एक्सपेक्टेशन वैल्यू ऑफ S1 डॉट S2 and you have a modulus and k is some constant and in front of that you have a minus sign representing say attractive nature. However, S1 dot S2 depends that value depends upon whether they are parallel or anti-parallel. If they are parallel, you will get large value. If they are anti-parallel, this value will be small. कर लोगे ये वाला? नहीं? Yes,
Yes,
or no? Okay.
सर
हाँ जी.
अभी जो आपने एक्सप्रेशन दिया था S1 डॉट S2 जब करेंगे बाहर मॉड्यूलस है ना, तो
Exactly.
वैल्यू सेम ही आएगा ना.
पहले बताओ, टू स्पिन है दोनों का, नेट स्पिन एस क्या लिखेंगे हम? S1 plus S2.
प्लस S2. यस.
Okay. And from here, if I write that expression for S1 dot S2, if first of all you do square both sides, है ना? If I square both sides, so for net spin S will be sum vector sum, and if you square both sides, then you will get, यहाँ से अगर स्क्वायर करोगे, कर लेना आप लोग, है ना? इतना तो करना ही चाहिए आप लोगों को. S1 dot S2 that value will get S square minus S1 का स्क्वायर minus S2 का स्क्वायर डिवाइड बाई 2, है ना? And you know when S square act on psi, it will give eigen value क्या देती है? S plus on H cross square psi, right? And you'll have S on square, it will give S on plus on H cross square psi, all right? And same is true for S2 square. You know, I'm giving some trick and I'm asking you to do by yourself. Why? This is some, I mean, you are my student, right? So I always to guide to student, है ना, कि आप थोड़ा सोचो, है ना, आप थोड़ा इमेजिन करो, क्योंकि you know that knowledge or I mean talented जो बोलते हैं लोग, it's not like that you are reading. हाँ, according to Einstein said if you have good imagination power then you are genius, है ना. मेमोराइज करके कोई जीनियस नहीं होते, है ना. So I am giving you hints, then I am asking you do by yourself. So if you will do, then you will imagine, you will think something, ना, and that will helpful, ना.
सर इसके आगे का
हाँ बताओ,
अभी समझ में आया, मतलब सब्स्टिट्यूट करके वैल्यू
कर लोगे ना?
हाँ ट्राई करते.
Okay, very good. Okay, so from where you will get that expectation value, that depends upon this, and S depends, this value depends upon whether they are parallel. अगर दोनों पैरेलल है तो S नेट S कितना हो जाएगी? ऑन हो जाएगी. If दोनों एंटी पैरेलल है then net S will be how much? That will be 0.
0.
So this expectation value basically depends upon this value, right? है ना. इनका दो वैल्यू पॉसिबल है, एक है जब दोनों पैरेलल है, दोनों एंटी पैरेलल है, it will be 0, right? So that's why Fn that will depends upon whether they are parallel or anti-parallel. Is this clear? If it is clear, then I'll proceed. I'll do some radioactivity. Then I'll go to nuclear model. That's not a problem. Okay, now we'll go discuss about that radioactivity. Something I'll discuss. Then I'll come to nuclear model. Okay. So how much time is there? Only 5 minutes are there. So कल से start करते हैं नहीं? Or I can do. Tell me.
करिए सर स्टार्ट एटलीस्ट.
Yes, sir. Call, sir.
Okay. Okay, let us I mean give that introduction. Radioactivity. Okay, you write first the phenomena in which in which unstable or excited nuclei, the phenomena in which unstable or excited nuclei comes to ground state, the phenomena in which unstable or excited nuclei comes to ground state by the emission of alpha comma beta comma gamma particles. So alpha comma beta and gamma particles. The phenomena in which unstable or excited nucleus comes to ground state by the emission of alpha comma beta and gamma particles. This phenomena is called basically radioactivity. है ना? ठीक है ना? So this process is actually natural. That radioactivity is actually natural process. Radioactivity. What is the meaning of natural? Is spontaneous process. Radioactivity is basically spontaneous process. Okay. Radioactivity is basically spontaneous process. Okay. So what is the meaning of spontaneous? It will basically happens automatically, right? It will basically happens automatically. Okay, but there is various cause of radioactivity. I mean, if you ask me what is the cause behind radioactivity or this decay process, there are basically various processes. So I'll discuss one by one. So you understood now? So this phenomena in which that unstable or excited state nuclei will come to ground state, that process is radioactivity. And there are various causes. So if I write one by one. So first of all, you have type of decay. Types of decay. Then we'll have example. And then we'll have cause or reason behind that. किस कारण है decay होती है ना? ठीक है. So first type of decay is known as alpha decay. And that will happen. Alpha decay is basically used to happen when you will have Z number of parent nuclei is greater than 83 and mass number of the parent nuclei is greater than 150. Then there will be decay, and that is called basically alpha decay. ठीक है ना? तो अल्फा डिके यहां से आप क्या समझ में आ रहे हैं आपको कि अल्फा डिके होगी जब आपका पेरेंट न्यूक्लियाई का एटॉमिक नंबर इससे ज्यादा हो और मास नंबर 150 से ज्यादा हो. इसका मतलब जब आपका साइज ऑफ द न्यूक्लियस इज लार्ज, राइट? मास नंबर 150 मतलब साइज ऑफ द न्यूक्लियस इज लार्ज. And this is alpha decay. And alpha is basically what? Alpha में क्या content है? The composition, you have 2 protons and 2 neutrons, right? And it's basically called helium 2 plus ion also, right? And example of alpha decay, if I give, suppose you have a parent nuclei atomic number Z A undergo alpha decay, so you have a alpha particle. And you have a daughter nuclei, there is a production of daughter nuclei. इसका atomic number कितना हो जाएगी? Z minus 2, right? And mass number will be how much? A minus 4.
-4.
And the reason behind this radioactivity is what? क्या reason है इसके पीछे?
Spontaneous.
No, why this decay is happening? That's why I'm asking. So the process or you have a large size of the parent nucleus is large. We have learned from that binding energy per nucleon curve, right? When you have large size nucleus, binding energy per nucleon is actually low. It means they are not stable, right? So the reason behind alpha decay is the size of nucleus of parent nucleus is too large. Okay, and from here I'll proceed tomorrow. Huh? Already time over. Okay. Shall I stop here?
Yes, sir. Thank you, sir.